have no idea. So I think one of the default that my laptop had.
Windows 8 is not meant to be put on a regular laptop.
I hate Windows 8.
If you ever use like a Surface or something, it's actually very nice.
Well, no, well, I have an Asus. It's a touchscreen, but I don't like Windows 8.
It's terrible.
It's like two different operating systems,
It is.
and it's like this is unnecessary.
You should have just separated them. I've been that for a really long time. I kept it that way.
I mean, make it easily syncable with other things, but don't. I mean, because it's hard to get. It's hard to network with the Windows 8 thing. PC, because all your other PCs aren't Windows 8.
Okay, you guys are doing okay? All right. Like I said, I'm going to give you your exams back in the middle when we take 5 minutes break. All right. So what I want to talk about. Oh, by the way, do you guys have any homework questions at all? Okay. This Friday you'll have another exam which will cover everything that we do till tomorrow, and then I wouldn't be answering very many questions until tomorrow, and then on Thursday I will answer your questions. But you can ask questions, general questions which are not homework questions, okay? But I'll answer homework questions on Thursday. So today what we want to cover is the topic composition of functions, and after we finish talking about this, we will start talking about limits, and that will be the start of calculus. So here's the definition of composition of functions. So it's an operation where you combine two functions together into one. So let's let f and g be functions let f and g be functions. Define the composition of f and g by f circle g. So f circle g will denote this new function, the composition of these two functions. And this new function, I need to tell you what it does to x. So if you give this new function an input x, how does it calculate the output? Well, what it does is that it calculates the value of g of x first, okay? And then whatever the value of g of x is, it calculates the value of the function f at g of x, okay? So the composition of f and g is equal to f of g of x. So you're evaluating g at x first, and then you're applying f. In other words, if I start with a value x, I am applying the function g to x, and I am getting, let's say, a value y, which is denoted by g of x, right? And then once I obtain the value y, I apply f to that value y, and then I get the value, let's say, z, and z is the value which is f of y. I'm sorry? Yeah, y is g of x, yeah. Yeah, go ahead. Yeah. Everybody is clear on the definition? Okay, we'll do a few examples to be more clear. Before I do that, let's talk about the domain of this composition function, okay? So f and g are two individual functions. Each one has a domain, right? And each one has a range. What is the range of a function? The range of a function is the collection of all different outputs, right? And so each of these functions, f and g, they have a domain and a range, okay? The question is, what's the domain of this new function, which is the composition of these two functions? Now, notice that when we evaluate the composition at x, the first thing we are doing is we are calculating g at x, right? So x has to be in the domain of g, right? Otherwise, you cannot evaluate g, right? So first thing to notice here is that x has to be in the domain of g because you're applying g to x. But then, you are applying f to g of x, right? Well, then you have to have that g of x is inside the domain of f, right? So the domain of f composition with g is the set of values of x, set of values of x inside the domain of g, for which g of x is inside the domain of f. So the domain of f circle g is the set of values of x in the domain of g for which the corresponding value of g of x is in the domain of f. Okay, let me give you a picture to see what's going on here. So let's say let's say the points inside of this circle represents the domain of g. Okay, so this is the domain of g. Okay, and let's say here this is the range of g. Okay, range of g. So points inside the second circle represents the range values of g. So if I pick an x value here, right, that x value is going to some value y, which is the value g of x, right, in the range. Now the function f, okay, the function f has a domain. So let's say the domain of f looks like the following. So this is how the domain of f looks like, let's say. And the domain of f is the collection of all points inside the circle. I am representing the numbers with the points there. And then let's say this circle here represents the range of f, right? Range of f. So once I get the value of g of x, I apply f to it. And I obtain the value z, which is f of y, right? Okay. And so what we have is that y is g of x, and then z is f of y, right? And so the domain of f is what? You see, if you look at the range of g and the domain of f, what's the intersection of the two? This area here represents the intersection of the domain of f with the range of g, right? So whatever the values of x you pick, the corresponding values, range values for g would have to be inside the domain of f, right? That's what we said. So let's say that this portion of the domain of g, okay, this portion of the domain of g, if you pick an x in the highlighted domain of g, for those values of x, the corresponding range values will be inside the domain of f. Let's say the points here will go to the points here. But those points are not in the domain of f, so you cannot apply f to them, right? So then, the only time you can apply f to g of x is when g of x lies here, and when you pick x here. Am I making sense? And then it works. So the domain of the composition is not everything in the domain of g. It's only part of the domain of g for which the corresponding range values will be inside the domain of f. Okay? Is everybody clear? But it is that the domain of the composition is part of the domain of g. Okay? All right, let's see this through some examples. Let's say I have the function f of x is equal to x squared plus 1, and let's say I have the function g of x that's equal to x minus 3. So let's see what's the composition of f and g. The composition of f and g evaluated at x, by definition, this is f of g of x. Okay? And then, what is g of x? So I'm going to plug in g of x first. What is g of x? G of x is x minus 3. And then what is f of x minus 3? You replace x by x minus 3 in the definition of f. What do you get? X minus 3 squared plus 1. So that's the composition. That's the composition of these two functions. Now, I forgot to tell you this. Whenever I have a composition of two functions, one of them is called in the inside of the composition, the other one is called the outside of the composition. So the function g here, is called the inside. This is called the inside of the composition. Inside, and this is the outside function. Outside function. This is the inside function. Okay? However, notice that if I change the order of the two functions, so instead of taking f circle g, if I take g circle f, evaluated at x, g circle f evaluated at x, then this is the same as g evaluated at f of x. Now the inside function is f, not g. Okay, that's the difference. Now what is that equal to? Well, I'm going to have to plug in f of x, which is x squared plus 1. And then I have to figure out what is g of x squared plus 1 is. Well, g of x squared plus 1, you replace x by x squared plus 1. In the definition of g, you would be getting this, which is x squared minus 2 at the end. Everybody's okay? So g circle f and f circle g, are they the same or different? Different. In general, remark, in general, g circle f is not the same as f circle g. Okay, generally these two compositions are not the same. They are different. What's that? What is our k? Oh, our k means remark. Yeah. RK, I write it for remark, yes. Oh, x squared plus 1 minus 3, so 1 minus 3 is a minus 2.
So there's no...
No. I wrote parentheses, I didn't need parentheses here. I wrote parentheses to make sure you understand that I am plugging in this thing for x here. Okay. Any questions on the example? Now, when do you think f? Can you give me an example of a function? Can you give me examples of two functions f and g, so that f circle g and g circle f are the same? Yeah, very good. So if you take f of x and g of x to be the same functions, right? For example, if I take f of x to be x and g of x to be x, right? Then if you take the composition, you get the same thing, right? So in that case, they will be the same. So I'm saying sometimes they might be same, but usually, in general, they are not equal. Okay, let's look at another example. Let's say I am taking the function f of x to be the function 1 over x minus 1, and I am taking the function g of x to be the function 1 over x. Okay. Do you guys remember the difference between the what's the graph of 1 over x minus 1 and what's the graph of 1 over x? You guys remember those graphs? There are two parts to them, right? Well, maybe I'll draw them. Let me draw them. Say it again. Yeah, you have to translate that. Yes. Okay, so the graph of 1 over x looks like the following. It comes down like this on this part, and then it looks like this here. And the graph of 1 over x minus 1, you translate the graph of 1 over x where? 1 unit to the right. Oh, sorry. Let me use a without arrow. So this is where 1 is, right here. And then it looks exactly the same as the other one, is just translated. Everybody gets the idea? Okay, this is the graph of 1 over x minus 1. This is the graph of 1 over x. Okay, let's say my question is, what's the composition of f and g, and what's the domain of f and g? Oh, sorry, what's the domain of the composition of f and g, okay? So the question is, find the domain of the composition of f and g. Now, can someone tell me what's the domain of 1 over x? So everything besides 0. And for the other one, it's everything besides 1. Okay, so we know the domain of the individual function, so we need to find the domain of the composition. So what did I say? What's the domain of the composition? It's the domain of the composition is all values of x in the domain of g, the inside one, for which the range values are in the domain of f, right? Yeah. The domain? Well, let's we have to be careful to say that. So I know that I can take the value, the domain of this guy to be. So first of all, we take the domain of g, right? And from the domain of g, we examine if I have any values in the domain of g for which the corresponding range values are not in the domain of f, right? Am I making sense? So what values are not in the domain of f? 1. So I need to figure out, is there a value of x in the domain of g for which I get 1 as the range of range of g? When x is 1, right? When x is 1, you get when x is 1, you get the value 1, right? So when x is 1, in the domain of g, when x is 1, the range value is 1, which is not in the domain of f. So I have to exclude that from the domain of f circle g. So then what's the domain of f circle g? Domain of f circle g would be everything except 1. Everything in the domain of g except 1, which says that I have to exclude 0 as well. Okay, so everything in the domain of g. So everything. So this would be the everything in the domain of g, such that g of x is not equal to 1, right? Okay. And so then everything in the domain of g, from the domain of g you exclude 1, so what do you get? Negative infinity to 0 will remain, right? And then from there you have to go from 0 to what? 1, and then you go from 1 to infinity. 1 is excluded. Okay, is that making sense? All right. Okay, now what is the composition of f and g? The composition of f and g is the same as f of g of x which is equal to f of g of x is what? 1 over x. And then I have to plug in 1 over x in the definition of f. So what is f? Very good. Minus 1, right? Okay, we have to simplify this a little bit. This is equal to 1 over x minus 1. That's the same as 1 minus x over x, right? And then this is equal to, yes, x over 1 minus x. Everybody is okay with that? All right. Another example. Let's say I have f of x is x squared minus 7 and g of x is 5 minus x squared. So then let's find out the values f of g of 1. What is that value? Well, f of g of 1, that's the same as, what is g of 1? What is g of 1? 4. And then what is f of 4? Yeah, so that's 16 minus 7, which is 9. Right? 16 minus 7. Okay, what is f of g of negative 2? Well, what is g of negative 2? What is g of negative 2? 1. And then what is f of 1? Negative 6, right? Negative 6. Okay, and one more. What is g of f of, oops, what did I do? F of 2. Well, it is g of f of 2 is what? Negative 3. And then g of negative 3 would be 5 minus 9, which is what? 5 minus 9 is negative 4, right? Everybody's okay? Making sense? Okay. Okay, so this is it for composition of functions. There are more examples that I could do, but these are all similar. Given two functions, find their composition and so on. Oh, maybe I should do one more example. First of all, let me make a remark. Sometimes you will see things like F circle G circle H, right? What does that mean? If I take the composition of three functions, what does that mean? Yeah, first of all, you should think of this as F circle with G circle F, G circle H. So I'm thinking of this, G circle H is one function and F is one function. So first of all, you take the composition of G and H, and then whatever you have, you take the composition of F. That's what it means. But if I evaluate this, let's see what I get. It means that it'll be f of G circle H, this function evaluated at x, and then G circle H of x is what? It's G of H of x. I hope I have enough parentheses. Okay? So that's what we mean. If you see that, that's what it means. Okay? F of G of H of x. Okay? Now the domain of the composition is part of the domain of which functions? Which of the functions? the domain of the composition of FGH is inside the domain of which function? No, only H. Yeah. Remember, if I have composition of F and G, the domain of the composition is inside the domain of the inside function. But you cannot take all of them. You have to make sure that the corresponding range values are in the right domains, right? Is everybody okay? All right. You might need this when you do your homework, okay? Should I do an example of three functions, or you can see what to do? Okay. So let's say I have f of x is x squared, g of x is 1 plus x, and h of x is root of x. Okay. Whoops. Okay, so then what is f circle g circle h of x? We know this is the same as f of g of h of x. 1, 2, I need one more. Okay, so what is that? Well, f of g, what is h of x? So that's what I'm going to plug in first. Root of x. And then, what is g of root of x? It's 1 plus root of x, right? You guys agree with that? G of root of x would be 1 plus root of x. And then what is f of 1 plus root x? 1 plus root x whole squared. Is everybody okay with that? Okay. It's not hard, it's just a little bit more writing. Okay, so that's it for I think this is section 1.3, I believe, that I finished. Let me make sure. Yeah, so this is section 1.3 that I finished. Yesterday, I think I already gave you the homework for section 1.3, right? Okay. So what we are going to do next is start section 1.4 and then move on to limits, okay? Any questions at all? Everybody's clear on composition of functions? Okay. The next thing that I'm going to be talking about is limits. Okay, and this is probably the most students find the concept of limit to be a confusing one or a hard one. So pay attention, and when you look at limits for the first time, you need to look at it a couple of times. Okay, you just have to look at it over and over again until you feel comfortable with limits. Okay, so the more exercise you do, the better you will get at understanding this limits. If you understand limits very well, life gets easier in calculus. Okay, if you don't understand limits, then it might not be that easy. The reason is, what separates calculus from algebra is the concept of limit. Everything in calculus, if you look at every single definition in calculus, underlying each definition there is a limit. Okay, so limit is everywhere in calculus. Okay, without the limit, you wouldn't be having calculus. So what makes calculus different from algebra is this concept of limit. Okay, and you'll see that once I start talking about limits, you'll see that everything else that we do has something to do with limits. Okay. So the topic is section 1.4, and we are going to talk about limit of a function. This is section 1.4. In section 1.4, though, I'm not going to define for you the limit of a function yet. I'm going to give you two motivating examples to start with. The first motivating example that I want to use is the following example. Let's say I have the function f of t, and the function f of t is the function t squared. Okay, very simple function. And the graph of this function is the same as the graph of the equation what? Y equals to t squared, which is a parabola, right? So let me sketch the parabola here. Okay, if I can do a good job on drawing the parabola, I have a hard time drawing on this tablet. So I'm already having trouble drawing it, but okay, so let's say this point here, is the point 1, 1, okay? So right here I have 1. The height of the point is 1 as well. And let's say I want to find the slope of the tangent line to this at this point. Slope of the tangent line at this point. So let me try to make a tangent line here. So let's say that's the tangent line at that point P. Let's call that the point P, and the point P has coordinates 1, 1, right? The question is, what is the slope of the tangent at this point P? Okay, so that's the question that we want to answer. What is the slope of the tangent? What's the slope of the tangent line at the point P to the curve y equals to t squared, right? That's what we want to know. Now, how do I answer that? In order to answer this, we are going to do the following. I am going to make what we call secant lines. So I'm going to pick other points on the parabola and look at the line segment between P and that point, okay? So let's say I pick a point here. So let's say I pick the point here Let's call that point Q. And the coordinates of Q, let's say, are t and t squared. So I'm taking an arbitrary point on the parabola. So the point, the value of t, let's say right here. Is everybody clear what I mean by Q? I'm picking a value t, and then I'm picking the corresponding point Q, which is t squared, right? Because it's on the parabola. If the first coordinate is t, the second coordinate would be t squared, right? All right, so this is, I'm going to call that a secant line, okay? Now, look at the line segment between P and Q, okay? And can someone tell me what's the slope of the line segment P and Q? So I'm going to let m of t be the slope of the line segment PQ. Slope of the line segment PQ. Can someone tell me what is the slope of the line segment from P to Q? What is the slope of the line? Yeah.
T squared
Yeah.
minus 1 divided by d.
Yeah, it's the rise of run. You subtract the y coordinates divided by, you subtract the x coordinates, right? The difference of y coordinates divided by difference of x coordinates, right? So that's the slope. So I get this, that the slope of the line segment PQ is t squared minus 1 divided by t minus 1. Everybody's okay with that? Notice that m of 1 is undefined, right? M of 1 is undefined, because if you replace t by 1, what do you get? 0 divided by 0, right? Now, one thing you need to realize here, that then now think about the following. Now let's allow t to approach 1, okay? So let's allow t to approach 1, okay? And if t approaches 1, then notice that the point Q will approach the point P, right? It will get closer and closer to the point P. And as the point Q gets closer and closer to P, what is happening to the line segment PQ? It is getting closer to which line? The tangent line, right? So if I allow t to approach 1, the point Q is going to approach the point P, and the line segment from P to Q is going to approach the tangent line, right? So that is, you know, if I pick a different value of t, then the line segment would be from here. I have a bad graph here, but the line segment P to Q would be here, right? The new position. Okay. So if you allow t to approach 1, then that's what's going to happen. So let me say it this way. Notice the closer t is to 1, the closer Q is to P, and the closer the line segment PQ is to the tangent at P. So then I could say that as t approaches 1, the slope m of t, which is, remember, t squared minus 1 over t minus 1, the slope of the line segment PQ approaches what? Approaches the slope of the tangent. It approaches the slope of the tangent line. Is everybody okay? You guys would believe that I have the line PQ, the slope of the line PQ will approach the slope of the tangent at P, tangent line at P. So now I have to figure out the following, right? When T is close, so we see that as T gets closer and closer to 1, the value of this fraction is getting closer and closer to the slope of the tangent line, right? You guys are with me here? So I'm saying as T gets closer and closer to 1, the value of the fraction is getting closer and closer to a number, and that number is the slope of the tangent. And even though this function is undefined at 1, right? The slope of this fraction is undefined at 1. So I need to figure out that. So so how do I find out? How do I answer that? How do I find the value? As T gets closer and closer to 1, the fraction is getting closer and closer to a number, and how do I find that number? Okay, so let me write that down. As T gets closer and closer to 1, the value of the slope of PQ, T squared minus 1 over T minus 1, is approaching the number L, let's say, and that's the slope of the tangent, okay? Slope of the tangent. And how do I find that number L? Okay, that's the question. Well, we know how to find the value of L. Anyone can guess what's the value of L? Can anyone guess the value of L? Well, let's study the function m, right, and see the behavior of this function. The function m of t is t squared minus 1 divided by t minus 1, right? Notice that I can factor out the numerator as this, and this is equal to t plus 1, right? So what's the graph? What's the graph of this guy? The graph of t plus 1 is what? Let's say this is one of the points. When t is 0, you get this point. When t is negative 1, you get this point here. And so this is a straight line that goes through these 2 points, right? Okay, and when t is 1, what's the height of this curve? 2, right? Because you have 1 plus 1, and this is 1 here, but the graph of m of t is what? The graph of m of t is the same as the graph of the line, except that you have a hole at 1, 2. Now notice that as t approaches 1 from either side, the value of m of t is closer to what? As as t approaches 1, notice that the value of m of t is approaching 2, right? So the slope of the tangent line should be what? 2. The slope of the tangent line should be 2. So the slope of the tangent line is tangent line at P is 2. Everybody's okay? Now we write this by using this symbol. We say that the limit as t goes to 1 of the function m of t, which is t squared minus 1 over t minus 1, we say that the limit is 2. Okay, we say that the limit of this function is 2 at 1. It means that as t gets closer and closer to 1, the value of the fraction is getting closer and closer to 2. Okay? The value of the function is getting closer and closer to 2 as t gets closer and closer to 1. Okay? So that we express this, remember we said as t goes to 1, the m of t goes to 2. Another way of writing that is by using this symbol. Okay? Yeah, go ahead. I didn't plug in any numbers. Where did I plug in numbers? From the graph, right? This is the graph of the function m of t, right? This is the graph of this fraction. It's the straight line with the hole at 1, 2, right? So then, from the graph, you see that as t gets closer and closer to 1, right? When t is very, very close to 1, the value of the function is very, very close to 2, right? So that's what we are saying. We didn't evaluate at 1. That's important because the function is undefined at 1, right? The fraction, this fraction value is undefined at 1, right? When you plug in 1, you get 0 divided by 0. That's undefined. Okay. Now, I am not yet showing you how to compute limits. Don't worry about computing limits yet. For now, we are computing the limits from the graphs. Okay. Later on, I'll show you how to compute limits. So that's going to be going to come later. Okay. But what I'm trying to motivate here is that why limits are important. Well, where limits came from? Well, one of the classic problem was, you have a circle, then you know how to find the if you have an arbitrary curve, right? You need to know the slope of the tangent lines to those points, right? And you might say, why do I care about tangent lines? Well, the reason is, think about the curve being the position function, okay, of an object. Then wouldn't you want to know the velocity of that function? Well, if you want to know the velocity, what's the speed? Well, that's given by the slope there, absolute value of the slope. Am I making sense? So, well, since I've already talked about, let's just say a few words about the that problem, velocity problem. So another classic problem is finding instantaneous velocity. Okay, so another classic example. So let's say I'm going to now use the same example, but I'm going to be talking about p of t being t squared, and let's say t squared P of t is the position of a moving object. Let's say you have an object which is moving on a straight line. Okay, so let's say I have the real number line, and here is the origin 0. Okay, and then P of t tells you the position of the object at time t. Is that making sense? P of t tells you what's the position at time t. So P of t is the distance from the origin of the object. So let's say you have an object which is moving on this straight line, and P of t is the position of that object, which is given by t squared. Now, you would then want to know what's the instantaneous velocity at time 1. Okay. Instantaneous velocity is not the same as average velocity, right? So what's the instantaneous velocity at time t? Okay, and well, what should be the answer? What should be the answer? Well, it should be the same as what I had before too. The reason is, let's go back to that example here. Now think of this function t squared giving you the position function, right? When we found the slope of PQ, right? What is the slope of PQ? What does the slope of PQ represent? We took the slope of PQ, that was t squared minus 1 divided by t minus 1, right? It represents, what I'm saying, what does it represent? That is, you see the position at time t, the position at time t is t squared. The position at time 1 is what? 1. So if I look at look at the time interval. So if I ask you what's the average velocity? What's the average velocity between time 1 and t? Between these two times, what's the average velocity? Anyone? Let me call that A of t. Well, average velocity, position at time t, position at time 1. You subtract for the net displacement, right? So that's going to be t squared minus 1, and then you divide by the length of time interval, right? If I say that your position, let's say you're walking on a straight line, your position at time 1 is, let's say 20 meters, and let's say your position at time 4 is 60 meters, right? What would be your average velocity? Well, you subtract 20 from 60 and you divide by your time interval 3, right? So this would be, you divide by time interval t minus 1, right? Between time 1 and t. So that's the average velocity, right? You guys realize that? Well then, what's the instantaneous velocity at time 1? Well, we do the same thing, right? We take the limit of this guy as t goes to 1. We want to know what happens to the average velocity as t gets closer and closer to 1, right? You guys get that? So this represents the average velocity between time t and time 1. So as t approaches 1, the average velocity will approach the instantaneous velocity, right? You're shrinking. As t approaches 1, you're shrinking the time interval to 1, and then the average velocity will approach the instantaneous velocity. That's the idea. Is that making sense? Okay. So without this concept of limit, okay, we are saying that as t goes to 1, the value of this average velocity goes to 2. This is the limit. So this is the way we express it is saying that as t goes to 1, the value of the average velocity approaches 2. We saw that. And the way we express this, same thing, is by writing that the limit of a of t as t goes to 1 is 2. Again, it's loosely speaking, it means that the limit of a of t as t goes to 1 is 2. It means that as t gets closer and closer to 1, the value of the function gets closer and closer to 2. Okay? Okay, so without the concept of limit, you wouldn't be having the concept of instantaneous velocity or instantaneous speed. Is everybody okay? Okay, so this is the end of section 1.4. End of section 1.4. Everybody's okay? All right, let's take a break for 5 minutes exactly. When we come back, we will start 1.5. So plug in 1 here to get the slope. Yeah, that's right. But I haven't talked about how to compute limits yet. When I compute limits for you, I'll show you all the techniques to find limits without using the graph. So far, because I haven't talked about them, I'm pretty sure you might have seen this limit before. That's why you're saying that. No. Whatever the reason is, we will get there pretty soon. Okay. So right now we are getting our intuition from the graph. What should be the limit? I haven't yet defined limit. I've been speaking very loosely about limit in terms of the graph. So we'll do that pretty soon. Okay, so we will start to look at section 1.5 now. And this is where we are going to define the limit of a function. So this is the limit of a function now in section 1.4, recall that what we did. Okay, we had this function m of t, and that function gave us the slope of the line between p and q, and that function came out to be this. And then we said as t approaches 1, the value of this fraction approaches 2. And we saw that by looking at the graph of the fraction, right? And now, so what you're saying is that as t gets closer and closer to 1, the value of the fraction is getting closer and closer to 2. But that's a very loose way of saying expressing this phenomenon. Because how close, right? The question is, how close does m of t get to 2, right? And in order to be more precise, and again, if you don't understand the more precise thing that I'm about to say, don't freak out. Okay, just look at it a couple of times and try to make sense out of it. It doesn't affect all that much. But what I said so far is a very loose way of expressing this phenomenon of a function approaching a number as the domain values approach another number. More precisely, what I want to say is that let's take a let's say I have a real number line here, and I have another real number line, and this is my t-axis. Okay, this is my, let's say, t-axis, and this would be, let me call that y. So this would be my y-axis. Okay, now I'm going to so on the t-axis you plot the values of t, and on the y-axis you plot the values of y, right? Now let's say I have the number 1 here, okay, and let's say I have the number 2 right here. So what we are saying is that as t gets closer and closer to 1, the y value is getting closer and closer to 2, right? The question is how close? Well, to express that, here's what I'm going to do, is I can make the value of this fraction to be within any small number of 2. Okay? So you give me any small number, the smallest number you can imagine. Okay, let's call that epsilon. And you say that, hey, I want my y value, or my m of t value, to be within epsilon of 2. Okay, am I making sense? I can make the value of the fraction m of t to be within any small epsilon of 2 by choosing any t in a small enough open interval centered at 1. By picking, so let me write that down. So when we are writing that the limit as t goes to 1 of m of t is 2, what does that mean? Let me say means that that the value of m of t, can be made to be within any small epsilon by taking any t in an let me say this way, in a sufficiently small open interval centered at 1. So that's what I mean. I can make the value of m of t to be within any small number of 2 by picking any t in a small enough interval centered at 1. You might say, okay, so if you suppose that one of you gave me a small number epsilon, and I found a small enough interval centered at 1, so that anytime t is here, the value of the fraction is here. Suppose someone else is giving me a even smaller epsilon, So let's say someone else gave me an even smaller epsilon. So this is 2 plus epsilon prime, and this is 2 minus epsilon prime. Okay, epsilon prime is a little bit smaller than epsilon. Then I might have to pick a smaller interval centered at 1. Okay. So no matter how small epsilon you give me, I can always find a small enough interval centered at 1 such that whenever I pick t here, the value of the function would be there within epsilon. Okay. So that's what it means to say that the limit of m of t is 2. I can make m of t as close to 2 as I desire by taking any t in a small enough interval centered at 1. Okay. All right. So that's really the definition of the limit of any function. So let's now go up. Yeah. You're looking at the last line? Okay. Everybody's done writing it down? Okay, so let's let f be a function okay. Let L be a number. Let L be a number. The limit. Let A and L be number. Let me just say here, let A be a number as well. So A is a number here. The limit of f of t, or let's say f of x, as x approaches A, is equal to L. This means that f of x can be made as close to L as we desire by taking x in a sufficiently small open interval centered at A, except possibly A. So what I mean is that as x gets closer and closer to A, the value of the function is getting closer and closer to L, but what happens at A doesn't matter. So the function may not be even defined at A. Okay? So that's what I'm saying, except possibly A. So this means, again, it means that if you have two number lines here, one of them representing x, the other one representing y. Let's say L, y is f of x, let's say. Let's say this is L and this is A here. So then what I'm saying is that I can make f of x to be as close to L as I desire simply by choosing any x in an open interval centered at A. Okay? So that's what it means to say that the limit of f is L. Let me first give you a couple of examples where I'm going to use the graphs to explain what's the meaning of these limits, and then later on we will show. I'll show you how to compute limits for different types of functions without looking at graphs. So here's my first example. What's the limit? What's the limit as x going to 2 of the function x squared, let's say. Let's say that's what I want to figure out. So again, I haven't told you there is easy. I can answer this question very quickly in one line, but I want to show you the graph and see why the limit is 2. So this limit would be 4, okay? And the way I'm computing that is by plugging in 2 there, but that's going to come later. Let me justify this by using the graph. So here is the my x-axis. Let's say here is my y-axis, and the parabola looks like this, let's say. And let's say my scales are bad, but let's say this is the point 2, the height is 4. The height is 4. Okay. Now notice that this is I only drew the right side of the parabola, right? There is a left side here. Notice that as x approaches 2, when x is close to 2, let me just say this. I can make the value of the function x squared, right here the function f of x is x squared. I can make the value of this function as close to 4. I can make the value of this function as close to 4 as I want to, simply by choosing x close enough to 2, right? Right? So as x gets closer and closer to 2 from either side, the value of the function is getting closer and closer to 4. Okay? So that's why the limit of this function is 4. Is everybody okay with that? So we can make the value of x squared to be as close to 4 as we want to by picking any x in a small enough open interval centered at 2. Okay? Let's look at another example. Let's say I have the function f of x, and the function f of x is given by x squared minus 1 divided by x minus 1 if x is not equal to 1, and the value of this function is equal to 4 if x is equal to 1. So I'm saying that the value of the function is given by the fraction when x is not 1. When x is 1, the value of the function is given by 1. What's the domain of this function? Well, it is everything because it's defined at 1. And I'm saying the value of the function when x is 1 is 4, right? So the function is defined at every value of x. So, but the graph of this function looks like what? The graph of this function again will be a straight line like this. So let's say this number here is 1, okay? My scales are bad, so yeah, so this is, let's say this is 1, and then this is this is 2 height here, right? And what's the value of the function at 1? It's 4, right? So I get a point, the point 1, 4 is right there, right? So that's the point on the graph. This point, is this on the graph? No, there is a hole right here. So the graph of my function f that I have, the piecewise defined function that I have, the graph of the function is the straight line without the point 1, 2 with the point 1, 4, right? Without 1, 2 with 1, 1, 4. So 1, 4 is on the graph, but 1, 2 is not there, okay? Now, what's the limit? What's the limit of this function at 1? The limit as x going to 1 of f of x is what? Well, when x gets closer and closer to 1, right? The value of the function is getting closer and closer to what? Really? 4? See, remember what I said. We don't care what happens at exactly 1. At exactly 1, the value of the function is 4, right? Do I care about that? I don't care about that. What I care is the following. When x is close to 1, but not equal to 1. So when x is close to 1, the value of the function is getting closer and closer to what? 2. So the value of the function, notice that here is the if this is x, what is the value of the function? The value of the function is this height, right? This height is the value of the function. So as x gets closer and closer to 1, the height is getting closer and closer to 2. Okay? So this limit is 2, not 4. Even though the value of the function at 1 is equal to 4. Is that okay? All right. Another example. Let's say I have the function f of x. Again, a piecewise defined function. This is x squared if x is less than or equal to 1. Let's say this is x plus 1 if x is larger than 1. Okay? Let's ask the following question. What's the limit as x going to 1 of f of x? Anyone has a guess for the limit? What is this limit? Is it 1? Okay, let's see. Let's say 1 is right here, and when x is greater than 1, the value of the function is given by x plus 1, right? And the x plus 1, so let me use a here. Let's say this is x plus the graph of x plus 1, okay? Okay, so let's say this is the graph of oh, I'm sorry, yeah, I'm gonna take this to be height 2, okay? This would be height 2. So that would be the graph of that's the graph of x plus 1. Let's say, okay. Now, the function, what's the value of the function at 1? The value of the function at 1, I mean f of x. The value of f of x at 1 is what? 1. Because when x is 1, you have to use the first formula, right? So this point 1, 2 is not on the graph of the function, right? When x is greater than 1, the value of the function is given by the straight line, right? And then what's happening to the left of 1? To the left of 1, so when x is 1, the value of the function is exactly 1, right? So this is the value of the function at 1. So let's say the height here is 1. And then when the parabola looks like what then? The parabola looks like this, right? Again, I'm not worrying about my scale at all. So this is the graph, right? This is the graph of f of x. You guys understand that? On the left side of 1, I take the parabola. On the right side of 1, I get the straight line. Basically, what you do, you draw the straight line and you draw the parabola, and then delete the portion of the parabola to the right of 1 and delete the portion of the line to the left of 1, right? That's how you get the entire graph of f of x, right? Okay, now we are asking our question, right? What is, this is 1 here. As x gets closer and closer to 1, the value of the function is getting closer and closer to 1. Someone said it's 1. Is that right? Was that? Anyone else? So, from either side. Right, right. So notice that if x is approaching 1 from the right side, the value of the function is getting closer and closer to 2. When x is close to 1, but on the left side, the value of the function is close to 1. So that means there is, I cannot say that the value, I cannot say that I can make the value of f as close to 1 as I desire simply by choosing any x in an open interval centered at 1, right? I can't say that anymore. So in this case, say it again. Basically, when I talk about the limit as x goes to 1, I mean the limit as x goes to 1 from either side of 1. Okay? So when x goes to 1 from either side of 1, the value of the function is not going to 1 value, right? Depending on which direction it's coming from, it's going to 2 or 1. So in this case, we say that the limit does not exist. Limit does not exist. We are going to talk about one-sided limits pretty soon. And one-sided limit means what happens when x goes to 1 from the right. What happens when x goes to 1 from the left, okay? And in that case, so let me just say that here. When I have a situation like this, we express this by saying that the limit as x going to 1, when I say plus here, it means x goes to 1 from the right side of 1 of this function f of x is 2. And when I write the limit as x goes to 1 with a negative sign, it means x is close to 1 on the left side of 1. And then this would mean this is 1. Okay? Everybody's clear? Okay. Example. Okay, I'm going to bore you to death with all my examples, okay? So, but I'm going to go over all the examples that I possibly can. The limit as x going to 0, sine x divided by x. I am going to give you a proof of this limit later, but I'm just going to tell you for now that this limit is 1. And I'm going to show you, the only reason I'm going to give you is by showing you the graph of that, which sort of beats the purpose because, see, in order to come up with the graph of this function, okay? In order to come up with the graph of this function, you need to know what is happening at 0, right? When x is close to 0, what's the behavior of this function? You need to know that before you can draw the graph, right? So I need to know the limit before I can draw the graph. But what I'm trying to do here now, I'm justifying the limit by using the graph. You see my point? But I'm going to show you a proof of this limit later, okay? And let's say the height here is 1. And the graph, obviously the function is undefined at 0, right? So I have a hole at that point. And then the graph looks like the following, okay? Near 0, the graph of this function looks like that. If you look at your calculator, you'll see that that's the case, okay? So that's the only explanation I'm going to give to you for this limit to be 1, okay? This is a very important limit. We'll see later. This is not the graph of sine. This is the graph of sine x over x. Sine x over x, yeah. So that's different. I mean, think about this. It's not as x goes to infinity, right? Sine x, the value is always between -1 and 1, right? So when x gets bigger and bigger, the fraction is getting smaller and smaller, right? So when x is big, the value of this function would be very close to 0, right? Is that making sense? So it's not going to be like the sine, exactly like the sine graph. Okay. So here's another example. Let's say I have the function y, which is sine of 1 over x. Again, is this function defined at 0? No, 1 over 0 doesn't make sense, so sine of that doesn't make sense. But let's say I want to know what's the limit as x going to 0 of sine of 1 over x. And let me give you a graph of this. Okay, so this height here is 1 and this height here is -1. The graph of this function looks like the following, okay? It looks like the sine graph. What happens here as it gets closer and closer to 0, I have a bad way of doing this, so let me try to do that again, okay? So as it comes closer and closer to 0, it keeps vibrating, okay? But it never touches the y-axis. It keeps doing that, okay? But at 0 it's not defined, so it never touches. The graph doesn't touch the y-axis. Same thing happens on the right, okay? Same thing happens on the right. That so again, I have a really bad drawing here because of the tablet, but otherwise I'm a very good drawer, right? So it keeps. So my point is, you see, as x gets closer and closer to 0, both sides are vibrating like this, okay? But it's never coming to cross the y-axis, okay? So the limit is what? Does not exist. Because the value of this function is always doing like this, between -1 and 1, so it's not approaching a 1 number. It's not approaching 1 number, it's always going between -1 and 1. Yeah. Say it again? I'm not plugging in 0 for anything. Right? Oh, in order to find the limit of a function, you don't just plug in.
What about the first one?
There are some instances where you can find the limit by plugging in the limiting point. In some instances, that doesn't work. I'm going to talk about how to compute limits later, and we will see what to do, okay? But just because you plug in, so if you plug in x equals to 0, it's undefined, right? The value of the function is undefined, right?
Yeah, that's why it's not good.
That's not the reason why the limit doesn't exist, though. Because remember our example here, this one, not this one, yeah, this one, for example. Suppose I take the function value to be just a fraction, right? If the function is just a fraction, then it is undefined at 1, right? But the limit at 1 is 2. Just because the function is undefined at a point doesn't mean that the limit doesn't exist. You see, we don't care what is happening exactly at the limiting point. I don't care what's the value of the function at 0. What I care is what's the value of the function when x is close to 0. Is that clear? Okay. Okay, so we talked about the one-sided. Let me talk about the one-sided limit a little bit more. One-sided limits. So what we write is that the limit as x going to a plus of f of x, and let's say L is the number, okay. So what's the meaning of writing this? What does this mean? Okay, what does this mean? It means that f of x can be made to be as close to L as we desire by taking x sufficiently close to A on the right side of A, right side of A, except possibly A, okay? So when x is exactly A, what happens doesn't matter. What matters is when x is close to A on the right side of A. So once again, it means the following. I'm writing plus to mean that this means that x is approaching A from the right side. So whoops. So let's say here is A and here is L. I have two number lines. So what we are saying is that I can make the value of f of x to be as close to L as I want to by choosing x in an interval like this. It's not going to be centered at A. It's going to be like this. Okay, by picking any x in an open interval on the right side of A, okay? So that's the difference, okay? Similar, we define the left-hand limit in a similar way, okay? The limit as x going to a from the left side of f of x is L has similar definition. Has similar definition. Everybody's okay? This is called the left-hand limit, okay? This is called the left-hand limit. And the other one is called the right-hand limit, okay? Whoops. And this one is called the right-hand limit, okay? I guess you have a little bit of intuition what that means, right, in terms of graph. So let's just see a few more examples on right-hand and left-hand limits. Let's say, first of all, let's look at the limit as x going to 2 of root of x minus 2. Can someone tell me what that limit is? The limit is 2? The limit as x going to 2 of root of x minus 2, right? What's that? Okay, so you're saying that I am even dumb to ask this question because of what? You're talking about the right hand because I shouldn't even be asking you to find the limit, two-sided limit, right? Why is that the case? Well, if I look at the graph of this function, here is, let's say, 2, right? And then the graph of this function is like this, right? You shift the graph of root x by 2 units to the right, right? So the function is even undefined to the left of 2. So I cannot ask you what's the limit as x goes to 2 from the left. So I should be asking what's the limit as x going to 2 from the right. Well, what is that? Obviously what? 0, right? When x is going to 2 from the right side of 2, the value of the function is going to 0, right? Everybody's okay? What's that? This is the, you agree that this is the graph of the function? Well, what's the height of the graph at 2? So the height, see, the height of the graph is getting 0, right? Yeah. So the limit in this case is 0. Everybody's okay with that? Okay, so here, and let's look at another example. Yeah. Yeah, like I said, I'm going to tell you how to compute limits. I'm not really talking about how to compute limits yet. But you can, so whenever you are asked to find if you have a function given by only one formula, okay, and if you plug in the limiting point and you get an answer, you get a number, then that's the limit, okay. But that doesn't work. Remember when we had this piecewise defined functions. At 1 it was 4. At 1, if it is not 1, then it's the fraction. In that case, you'd get a wrong answer if you just plug in, and you'll get. So that's what I'm saying. If a function is given by only one formula, then when you plug in the limiting point and you get a number, that's the limit. Okay. I'll say those things in a bit. So let's look at another limit. The limit as x going to 0 of absolute value of x divided by x. What is that limit? Well, if you plug in 0, you get 0 divided by 0, so that means that the function is undefined at 0. Again, remember, we don't care exactly what happens when x is 0. The function is undefined, who cares? Because even if the function is undefined, the limit may exist. We saw that before. Yeah?
If I know the graph of the absolute value, how do I know the graph of the
Absolute value of x over x, right?
Yeah.
Okay, let's investigate this function a little bit more, okay? Can someone tell me what's the value of absolute value of x when x is positive? If x is already positive, absolute value of x is the same as x, right? So I get x over x, right? Which is the same as what? 1. 1. So this is what happens if x is positive, right? Okay. What happens when x is negative? When x, you know that x is negative, absolute value of x is what? Okay, but how do I make it positive? You see, I'm saying x is negative. So how do I make x negative? How do I make a negative number positive? The absolute value of x is negative x, right? When x is negative, is that making sense? If x is negative, you know, then if I multiply by x by a negative sign, then am I not making it positive? If x is known to be negative, multiplying x with a negative sign makes it positive, right? So when x is negative, absolute value of x would be negative x. Right? Absolute value of x means I want to make it positive, right? So this is equal to what? Negative 1. Let's see if you are sure what I said. Absolute value of x is x when x is positive. Absolute value of x is negative x when x is negative. Because if x is already negative, in order to make it positive, you can multiply by a negative sign. Now, what's the graph of this? This is a piecewise defined function, right? What's the graph of this function? Anybody? Let's say this is the x-axis, right? Let's say this is the y-axis. What's the graph of this? This is now a piecewise defined function. What's the graph of that? First of all, this function is undefined at 0, right? Okay. What's the graph? Yeah? Did you want to say something?
basically a line like that.
Exactly. So when x is positive, the value of the function is always 1, right? When x is positive, the value is always 1. When x is negative, the value is always negative 1, right? So the value of this function looks like the following. It's a straight line here. This is the height 1, and straight line here. This is height negative 1, and I have a hole at these 2 points, right? Because the function is undefined at 0. So now notice that the limit at 0 is the limit at 0 from the right is 1. The limit at 0 from the left is negative 1, which are not the same. So the two-sided limit does not exist, right? So now we could say that this limit does not exist. However, we could say that the limit as x going to 0 from the right is what? From the right is 1, and the limit as x going to 0 from the left is negative 1. Everybody is okay with that? So remark, the limit as x going to a of f of x is equal to L if and only if the limit as x going to a of f of x, f going to a from the right of f of x is L, and also the limit as x going to a from the left of f of x is L. So the two-sided limit is L if and only if both of the one-sided limits are L as well. Okay? Is that making sense? Both of the one-sided limits are equal to L if the two-sided limit is L, right? Is everybody okay with that? All right, so that's that. Say it again. Yeah. Right here. A little bit more. Yep. Okay, now I'm going to develop some tricks for computing limits. Okay. In some cases, you cannot escape. For example, in this case, right? Is there any other way of computing this limit? Well, this is what you have to do. In order to compute this limit, you have to get rid of the absolute value and write it in this way in order to come up with the limit. There is no other way of computing the limit of this guy. Okay? Everybody's done with this? Okay, so let's look at how we compute limits. The first thing I want to do is I want to know how do I compute the limit of a polynomial function at any given point. Okay, and the answer is very easy. First of all, let C be a constant. And consider the constant function f of x is equal to c. Okay? So then what's the graph of this function? Let's say, it's going to depend on whether c is positive or negative, right? If c is positive, right? If c is positive, let's say this height here is c. If c is positive, the graph of this function is the horizontal line at height c, right? Is everybody okay with that? Now let's pick any number a, right? Let's pick any number a in here. Then what's the limit at a? What's the limit as x going to a of this function? I'm going to just write c. What's the limit of this constant function at a? Y negative c. No, the value c is always c here, right? The value at a is still c, right? The value of this function is c no matter what x is. Was that? It's c, right? The limit is c, right? Because as x gets closer and closer to a, the value of the function is closer to c, right? It stays c, in fact. In this case, the value is always c, so it's got to be close to c. Okay, so this works for any a, right? No matter where I pick a, no matter what a I pick, this limit is always c. Okay, so now we know how to find the limit of a constant function. The limit of a constant function is just the constant, right? At any limiting point. Okay, now what's the limit as x going to a of the function x? What is this limit for any a? For any a, what's the limit of this function? By the way, what's the graph of this function? Okay, so this is the graph of this function, right? And let's say a is right here. Okay. Yeah, so the height here is also a, right? So this limit is a. Okay, so this is for any a. For any a. For any a, the limit of this function x is just a. Is everybody okay with that?
What if it's x wonderful?
I'm going to get there right now, okay? I'm going to answer your question right now. So here's some limit laws. Limit laws. Suppose the limit as x going to a of f of x and the limit x going to a of g of x exist. Let C be a constant. So when I write SPZ, usually that's short for suppose, okay? Not that I don't know how to spell suppose, right? It's just that if you do math for a long time, you start to abbreviate a lot of words, okay? Like IFF, it means if and only if, right? So SPZ, then we have couple of facts here. How do I find, suppose I know the limit of the function f and I know the limit of the function g, then how do I find the limit of f of x plus g of x? How do I find the limit of the sum? Well, the limit of the sum is basically the sum of the limits. So you take the limit of x, f, plus you take the limit of g. So given that the limit of f and the limit of g exist, given that the limits of these two functions exist, I can find the limit of the sum by adding the limits of the individual functions, okay? So I can take the limit of f plus the limit of g. What if I have a minus here? Then I have a minus here, okay? 2, the limit as x going to a. If I know, let's say I know the limit of f of x, how do I find the limit of c times f of x? Well, this would be the same as c multiplied with the limit, the limit of f of x. Okay, the limit of cf of x is the same as c times the limit of f of x. That is, you can factor out the constant out of the limit, okay, before you compute the limit. 3, what's the limit as x going to a of f of x times g of x? Well, that's the same as the limit of f. That's the same as limit of f multiplied by the limit of g of x. Okay? And what's the limit as x going to a of f of x divided by g of x? That's the same as the limit as x going to a of f of x divided by the limit as x going to a of g of x. But there is a condition though. This works as long as the limit in the denominator is not 0, right? Otherwise it wouldn't work. 5 for any positive integer n, the limit as x going to a of f of x to the exponent n, okay, that's the same as the limit x going to a of f of x to the n. So you can just raise the limit of f to n in order to get the limit of the function f of x to the n. Okay, everybody is clear, everybody understands these statements. Let's apply them and see what they mean. Yeah, give me 1 second. Yes. Yeah. No. Log laws, when you take calculus 2, you'll see they'll talk about the log functions in detail, and you'll see what are the log laws. I don't want to delve into that, but I'll show, if you, at the end of the class, if you want me to, I can show you the laws and show you the difference between the two. We are not, so log laws is about laws for a function. This is laws for limits, okay, so they are different. Okay, so let's start with an example. Let's say, so let's say I want to find the limit as x going to 5 of 2x squared minus 3x plus 4. So I want to find the limit of this guy, and notice that by our limit laws, right, if I have a sum, I can take the limit of individual summand and then add them, right? So this would be the limit of 2x squared minus the limit of 3x plus the limit of 4, right? And then remember, if I have a constant, I can take it outside of the limit. So this will be 2 times the limit as x going to 5 of x squared minus 3 times the limit as x going to 5 of x plus the limit. Well, last one, what's the limit of 4? It's a constant function, so the limit of 4 is 4. And here I get that this is 2 times. What's the limit of x squared? We can apply our fifth rule, and it says that this is the same as the limit as x going to 5 of x squared minus 3 times, the limit of x is what? Limit of x as x goes to 5 is 5. We saw that, right? Limit of x going to a of x is a. And this is here, I get 2 times, the limit of here is 5, so I get 5 squared minus 3 times 5. Oh, I forgot about 4. Plus 4. Is everybody okay? Everybody's okay with that? Questions? Yeah.
How do you get 3.5?
Not 3.5, 3 times 5. I'm going to multiply in a bit. I'm just waiting for you to write it down. You are going to multiply and simplify it out. But there is a reason why I stopped here, though. I'm going to show you something in a bit why I stopped here. Notice that what was my original function that I was taking the limit of? I was taking the, let me write that down here again. I was taking the limit as x going to 5 of 2x squared minus 3x plus 4, right? And the limit that I obtained is this, right? Let me use the eraser here to make it cleaner. So I obtained the limit to be this. Notice what I basically did was I replaced x by 5, right? After I applied all my rules, all I did really is plugged in 5, right? So generally, for any polynomial, that's valid. If I give you any polynomial function, in order to find the limit, all you have to do is plug in that limiting point, and that's going to give you the limit. Okay? So now I'm going to write that fact down, that if p of x is a polynomial function, then the limit as x going to a of p of x is p of a. Everybody's okay with that? Yeah, you can use that. Previous example, I sort of showed you why those limit laws were important, okay? But if you have a polynomial, you can just plug in, okay? Let me give you another example. The limit as x going to a of p of x is p of a. Let's look at another example. So the limit as x going to negative 2 of 5 minus 3x is going to be 5 minus 3 times negative 2, right? I just plug in because it's a limit, it's a polynomial, right? So what do I get? Oh, by the way, I forgot to compute this, right? What was that? It's 39. Okay. Let's look at another example. What's the limit as x going to negative 2 of x cubed plus 2x squared minus 1 divided by 5 minus 3x? Well, what's the limit of the denominator? We just computed the limit of the denominator, right? What was that? 11. It was not 0. So as long as the limit of the denominator is not 0, I am allowed to do the following. I can take the limit of the numerator, x cubed plus 2x squared minus 1, and I can divide that by the limit as x going to negative 2 of 5 minus 3x. And how do I find those limits? I just plug in, right? Negative 2 cubed plus 2 times negative 2 squared minus 1 over 5 minus 3 times negative 2, and I get what? I'm going to get 11 in the denominator, and the numerator I have negative 8 plus 8, so I get negative 1, right? Everybody's okay? Now notice once again that my fraction, when I plug in negative 2 for my fraction, I basically get the same answer, right? I mean, if you compare, if you look at this function here and look at the final answer that I have here, right? What did I do? I plugged in negative 2, right? Now, for a rational, so a polynomial function, I can always plug in to find the limit. But for a rational function, though, I can only plug in if the denominator is not 0. Otherwise, you cannot find the limit by plugging in. Okay? So, let me write that down here. If R of x is a if R of x equals to P of x divided by Q of x is a rational function, and A is in the domain of the rational function, then the limit as x going to a of P of x over Q of x is P of a over Q of a. So I can find the limit at a by just plugging in a, as long as a is in the domain of the rational function. What do I mean by that? It means that when I plug in a, I don't get 0 in the denominator, okay? So you can find, if I give you a rational function, you can just plug in, and if you get a number, that's the limit, okay? Is everybody okay with what I said? Okay. However, you cannot always plug in for a rational function, because there are some rational functions for which you can't just plug in. Here's an example. And we already looked at this example. Remember this example, limit as x going to 1 of x squared minus 1 divided by x minus 1. If I plug in 1 for x, what do I get? 0 divided by 0. If I have a rational function, and when I plug in, I get 0 divided by 0, then you don't know what the limit is, right? It doesn't mean that the limit doesn't exist. All I know that it's not telling me what the limit is. Now, whenever you get 0 over 0 for a rational function, the trick is factor out and cancel out some terms. So in this case, the trick is factor out. So you get x minus 1 times x plus 1 over x minus 1, and then you get, this is the same as the limit as x going to 1 of x plus 1, which is 2. Everybody's okay? Let me do another example similar to this one. Let me know if you're done writing it down. You guys, it's important to remember the facts I'm telling you. Okay, what I said is that if I have a rational function and when I plug in, I get 0 divided by 0, the trick is factor out and cancel out terms. Okay. Here's another example similar to this one. similar to this one, which is the limit as x going to 1, x squared plus x minus 2 divided by x minus 1. Okay, what do I get when I plug in 1? 0 over 0. Then what's the trick? Factor out. So in this case, if I factor out the numerator, do I get x minus 1 times x plus 2? And that would be the limit as x going to 1 of x plus 2, which is 3. Okay, sometimes when you get 0 divided by 0, you have to simplify first. Okay, whenever you have 0 divided by 0, you have a factor in the denominator which is giving you 0, right? Your goal should be to try to get rid of that. Okay, so here's an example. Here is an example. So let's say I want to find the limit as h goes to 0 of 3 plus h squared minus 9 divided by h. How do I find the limit here? Well, I could, if I want to, factor out the numerator, but I'm not going to do that. What I'm going to do is, I see that in the denominator I have the factor h, and which is giving me 0. Okay? Maybe I have, let's say, 3h, okay? So the factor h is giving me 0. I would want to get rid of that, okay? So how do I get rid of that? Well, in the numerator, I am going to simply simplify the numerator, okay? So what is 3 plus h squared? So it will be 3 squared, which would be 9, plus 2 times 3 times h, which would be 6h, plus h squared. So what I'm doing is I am multiplying out 3 plus h, right? You can FOIL if you want to. And then minus 9 divided by 3h. Is everybody okay with that? And this is equal to the limit as h goes to 0. 9 cancels out, so you get 6h plus h squared divided by 3h. And let me write it up here. This is equal to the limit as h goes to 0. I can factor out an h in the numerator. I get 6 plus h divided by 3h. And now h cancels out. Now if I plug in 0, what do I get? Let me write one more line here. The limit as h goes to 0 of 6 plus h divided by 3. And when I plug in 0, I get 6 plus 0 divided by 3, which is 2. Everybody's okay? Once again, note that the fraction that I have here, this is a rational function in h, right? You agree with me? This is a numerator is a polynomial in h, denominator is a polynomial in h. If I plug in 0 here, I did get 0 over 0, right? So again, whenever you have 0 over 0, you need to try to get rid of the factor in the denominator that is giving you 0, okay? All right, so we should be ending here. I have more examples and more limits that's coming up, okay? All right, so I think this is it. So you should really try to make sure you finish all your homeworks by today. that everything that I assigned so far. Okay, and if you have questions, you can ask me tomorrow and the next day. I'm going to be finishing limits pretty soon. So you'll have 1.5, 1.6 homework tomorrow. Okay. Those of you who didn't get the exam back, Hanishi, Faris, Sultan, Hanishi, Abdul Rahman. Somebody can take his. Sultan is not here. Okay, Salem. Who can take that? Faisal. Faisal.
He's not here. I can give him all.
Abdullah.
He's not here.
Abdullah Aziz.
Not here.
You can take him. Sultan, you can take him as well.
Salam.